derivatives. What theorem did we see last time? The very last theorem, Clairaut's theorem, which states that if you can switch the order of the partial derivatives, provided that the f12 and f21 are continuous, right? You remember this? Yeah? This is the very last thing we ever did. Clairaut's theorem. Right? Yeah? We've seen that? Great. So let us apply this. Suppose that f xy is a function satisfying f11 xy plus f22 xy is equal to 0 for all xy squared, and assume that f12 and f21 are continuous. Show that if USD is equal to f of x squared minus b squared 2xt, then let me change notation here. Well, we use our functions, okay? Okay? So this is did I start recording? Yes, I did, okay. Yeah, it is recording. Okay, so what do we need to do? What is a good way to start? The chain rule, right? I need to differentiate. Oh, this is u? Yeah. I need to differentiate u how many times with respect to s? 2. And I need to differentiate c how many times with respect to s? Let's do this. So what's the derivative of u with respect to s? What is this? Who can help me? Who can start? Who wishes to start? Or should I do it? Should I just do it? Let's see. So u, s, and t. I differentiate the first argument with respect to s. What do I get? Everybody? The first argument with respect to s, what do I get? To s, right? f1 x squared minus b squared 2st, right? Plus, what do I get after? What do I get after? Everybody? Who wants to help? No volunteer? Plus? Yes? Yeah? So set this be u and set this be v. So u is, well not u, a is s squared minus b squared, and b is 2st. So del u, del a, right? And del a, del t, plus del u, del b, del b, del t, right? What is the derivative? Plus what? The derivative, yes? Plus 2t times? Times? S2? At what point? Where do I evaluate S2?
Sorry?
Where do I evaluate S2? Here, right? Agree? Everybody, do you agree with this? Yes or no? Great. Now what do I need? I need to differentiate u with respect to x another time. We agree? What do I get? Who can help me? How to differentiate this term? Is this a function of s? Does this depend on s? So what do I use here when I differentiate with respect to s? The product rule. How do I do this? Product rule. Good morning. Yes.
F prime times G plus G prime times S.
Very good. So prime is with respect to s, right? So I differentiate this with respect to s. What do I get? 2, right? F1 to st plus I keep this one fixed, and I differentiate this term with respect to s. What is the derivative of this term with respect to s? What's the derivative of f1 with respect to s? How do I differentiate f1 with respect to s? It's a function. How do I differentiate with respect to s? You let this be, say, hst. How do I differentiate this one with respect to s? I take the derivative of this term with respect to s times the derivative of f1 with respect to the first argument applied at s squared minus t squared to st, plus the derivative of the second term with respect to s times the derivative of f1 with respect to the second argument applied at s squared minus t squared to st. Are we good or no? Yes or no? Yeah? Plus 2s plus t. So I differentiate the first term with respect to s. So I get 2s. What's the derivative of f1 with respect to the first argument? f1 is 1, right? Plus, what did I do here? Yeah, 2s. Now I differentiate the second argument with respect to s. What do I get? 2t. What's the derivative of f1 with respect to the second argument? f1, 2. Very good. 2st. And that's it. Now what do I need to differentiate? I need to differentiate this term with respect to s. How can I treat 2t? 2t is treated as a constant, right? 2t is treated as a constant. What do I do then? Any questions? Okay. How do I differentiate f2 s squared minus t squared with respect to st? With respect to, t? Derivative of first term with respect to s is 2s times derivative of f2 with respect to the first argument. What's the derivative of f2 with respect to the first argument? f2, 1. Very good. To st plus, what do I do now? Plus 2t times, yes, t, f2, 2, right? Now, I don't know if we need for the result to hold equal, but let's assume it, okay? So let me apply the result, because they might cancel out individually, but let's not worry about this. So let's do that. Right, you see that the symmetry is here, right? So let's regroup terms. Should we regroup terms? So what is USST? It's 2. So the thing I don't want to see is writing 2f1 without nothing, without arguments. Okay? So if you write 2USST as 2f1, it's not very right. Okay? You need to tell me at what point I'm applying f1. Okay? Where should you write this? I think then it should be clear that UTT will be minus that. Do you see why or not? Because if you switch S and T, anyways, let's not worry about it. So let's rework it out in a better way. That way you know. So what is 2F1? Well, let's write it here. 2F1 2xt plus 4x squared F11 as x squared minus t squared 2xt, right? Plus 4t squared F22 right? Is that right? Is that right? Yeah. So I took this term, then I took this term. Yeah. What else do I have? Plus, so 4xt F12 plus 8st F12 because F21 is equal to F12, right? You guys see this? I have 4st F12 and 4st F21. Those two can be added into 8st. You may be able to, I think, because you will have you may have cancellations after. Okay, but let's. Okay, all good so far? All good so far? Since F12 is equal to F21 as functions. Okay, so if they're equal as functions, then they're equal everywhere. So in particular, at that point, they're equal. Okay, are we good here? Yes, sir.
How do we know that they're equal?
I mentioned that they're continuous.
Oh.
Okay? Great. Now, what do I need to differentiate? U, T, T. You can rewrite the whole thing, or you can notice that if you flip S and T, you get for some reason. Okay, anyways. Right? Notice the symmetry, right? So if you flip S and T, what do you get? You're just flipping this term, right? You see that or no? And then this term is fixed. So you can differentiate that this way. Or we can redo it. What do you prefer? We redo it? Let's redo it. What's UT, S, and T? Oh shoot. What is US? UST is S squared minus T squared. Right? What is UTST? I differentiate the first term with respect to T, right? So what do I get? Minus 2T F1 of x squared minus T squared. And then what do I get? 2ST, right? Plus 2x, agree? F2 x squared minus T squared 2ST. What do I get afterwards? I need to differentiate with respect to T again. Derivative of 2t with respect to t minus 2t, what do I get? Minus 2 f1 x squared minus t squared 2ft. Notice when you add them up, what happens here? Try to add these up, what happens to these two? They cancel out, right? Because, right, they cancel out obviously, right? It's 2 f1 blah 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 minus 2 f1, the same blah blah blah, right? So they cancel out. Then what do I have here? Plus 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 plus. So I differentiate it. Now I need to differentiate this one with respect to t, right? And I keep the minus 2t fixed. How do I differentiate this one with respect to t? Who can help me? Yes?
Minus 2t, F11 of S squared minus 2t.
minus 2t, f11 s squared minus t squared 2st. Great, then?
Plus 2x.
Plus 2x, very good.
F12.
Awesome.
S squared.
Okay, thank you very much. Then I need to differentiate this term with respect to t. What do I get? The second term with respect to t. Who can help? Derivative of the second term with respect to t. What is this? 2s can be treated as a constant. So I say to take it out like that. I want to differentiate f2 s squared minus t squared 2st with respect to t. What do I do? Differentiate the first argument with respect to t. What is that? Derivative of the first argument with respect to t. What is it? Negative 2t. Times derivative of f2 with respect to its first argument, which is f21. Very good. 2st, right? Plus what? The derivative of 2st with respect to t, right? Which is, what is that? 2x. Times the derivative of f2 with respect to its second argument, apply that s squared minus t squared 2st. Notice you didn't need the mixed partials to be equal, right? Because you have minus 4st here and minus 4st here, and then the 1, 2, and 2, 1 will cancel out. But let's not worry about this. So what do you get? Let's write this. Plus or minus, well, the minus or plus? Let's see. So there might be a mistake here. What do I have for S11? So I differentiated this with respect to, oh, this is minus here, right? This is minus here, right? The minus right here. Okay, so what do I get? 4t squared. Right? You see that? You guys follow? Do you guys follow? 4t squared 2st. Now, how many s's do I have? 4s squared. Minus 2t plus 2s times 2s, this is 4s, minus 4s. Okay, and here you have minus 4s. f21 is equal to f12, so you get minus 8st f12. Did I use f12 here? Are we good with this or not? Are we comfortable with this? Are we comfortable? Are we comfortable with differentiation or not? Yeah? No? More examples? Is it clear or not? Is it clear what I'm doing or? No? It's not clear? Is the first derivative clear? Is this first step clear? Right? This first step is clear. Is it clear? Is this first step clear? Now when you go to the second step, you need to apply the chain rule again. And it's not magic. It's just the same chain rule. How do you differentiate a function of s and t with respect to x? Derivative of the first argument times derivative of f1 with respect to the first argument applied at this point, plus the derivative of the second argument with respect to s, times derivative of f1 with respect to its second argument applied at this point. Is it clear or no? Should we do more examples? Let's do more examples. Let's do more examples. Really, this because usually people just write del Z, del U, and things like that, or sometimes they drop the argument, they just write F2. Pardon me? Any questions? Any? Yeah, please ask.
I have a question okay, I understood how, like for U and S, I understood how the first two terms came. And however, for the third, like fourth term, so when we were doing UP prime, so for the UP prime of the second one,
okay.
we have to S squared minus T squared 2ST.
Okay.
Why is there something with S21?
Sure. This is clear.
Yes.
Everybody, is this line clear? Please let me know if it's not clear. Raise your hands if it's not clear. I'll explain it. Don't hesitate. This line is clear? Everyone, please raise your hands if it's not clear. Or just nod or something. Make a sign if it's not clear. The first line is clear, right?
Yeah.
Okay, great. Now I want to differentiate this line with respect to S again. Okay? I want to differentiate the first line with respect to S. Great. So it's a sum of two terms. Let's go back to basic differentiation. It's a sum of two terms. I have to differentiate each sign on its own. Great. Let me differentiate this one. Does this depend on S?
Yeah.
Does this depend on S?
Yeah.
What rule do I use? Product rule. Great. Derivative with respect to S of 2S, what is that? 2. And I keep the second term fixed. So far so good. Plus, I take this term, I put it here. Let's put a 2 here. 2S, and then I have to differentiate this term with respect to S. So far so good. Yes or no? Yeah? Are we following? Okay. How do I differentiate this term with respect to S? It's the chain rule again. But my S that I'm differentiating is F1. Okay, so let me just write this here. I mean, you know, is it okay if it doesn't appear on the recording, if I write it here, or you want to see it? It's okay? Okay, so let me write F1 S squared minus T squared 2ST. Let me write this as just F okay? Let me write this as F. So let me write this little f1 as big F. How do you differentiate this one with respect to S? How do you differentiate this one with respect to S? You take 2F, F1, right? S squared minus T squared, 2ST, plus 2T, F2, S squared minus T squared, 2ST. We agree or not? Everybody, do we agree with this? Are we good or not? Now, what is F1? What is F, sorry? F is F1, so write that. You see that?
Okay.
Erase big F, and then, okay? Is it clear now? Okay? This is how you do it. Is it clear or not? Okay? Maybe I should write this here. Okay, I mean, let's write this in case. So you like FST is equal to F1 to S. Okay? You differentiate this with respect to S. You get this 2S F1 S squared minus T squared 2ST. Okay? Plus 2T, right? I'm differentiating with respect to T. So that's with respect to S plus 2T do you do? What is big F? Big F is little f1. F1, and big F is little f1. Okay? Now it's clear? Now is it more clear? Great. Let's continue. F1, okay guys, there's too much talking. Thanks. So what do you do here? Where were we? We were here, differentiating this term. 2x f11 x squared minus t squared. So I kept the 2x I was differentiating this term, right? So I kept this term fixed. I differentiated this term. 2x f11 x squared minus t squared 2xt plus this term. Are we good now or not? Is it clear? Is it clear? Just, let your big F be little f1. Do it in terms of big F and just write big F is little f1. Okay? Now I have to differentiate this term. What rule do I use again? Is 2t constant with respect to s or not? Okay, so I can take it out. And what term do I have to differentiate with respect to s? This term, right? How do I differentiate this term? I take the derivative of, you can pick big F is equal little f2. We can now just do it mentally. So s squared minus t squared, how do you differentiate this with respect to s? What do you get? 2s times the derivative of f2 with respect to its first argument. What is the derivative of f2 with respect to its first argument? f21, s squared minus t squared 2st. Plus, you have this other part. Derivative of 2st with respect to s, what is that? 2t. Times the derivative of f2 with respect to its, second argument, which is f22, and so on. Okay? Are we good? Yes, sir.
Do more examples.
Sure, we can do more examples. Now, let's finish this one. Now, if you add USS, SSE, it's clear that plus UTT, what do you get? You get 4t squared f11 plus 4t squared f22 evaluated at the same points, right? What is that by assumption? 0, right? You see that? Plus 4s squared f22 plus 4s squared f11 evaluated at the same points. What is that by assumption? 0. You have minus 2 f1 here plus 2 f1 evaluated at the same point. What do you get? 0. You have 8st f12 minus 8st f12 evaluated at the same point. What do you get? 0. So the sum of these two is actually 0 for all. Okay? Yes, ma'am. Why is 0? By assumption, what did we say? We said that if you differentiate f with respect, you see that? By assumption, f11 plus f22 are 0, identical. Is 0 identical? Is this stuff clear or not? This is the chain rule. You should be very, very careful when you write stuff. You cannot just write 2sf1 plus 2tf2. I will just cross it. I will not read it. Okay? You have to specify the arguments at each time. So if you feel comfortable writing s squared minus t squared as u and v, sure, you can do that. But you have to keep the u and v at every single step. You write f1, this is 0. Okay? Means some people do it. I personally don't like it. And I think for a good reason. Because when you write minus 2s f1, what does it mean? Okay? It means nothing really. Well, it means something, but it doesn't mean, well, anyway. Great. Let's try and do one more example. But is this clear? Is this clear? Is it more clear than before what we're doing? So you can expect a question like that on the final as well. Okay? You can expect something like that on the final. Okay, so let's see if we find nice examples. Now 1 second, there it is. I mean, I guess we'll leave an example until later. We'll do examples later. Okay, so please, I'll give you maybe some problems to practice, or we can. Or you know what? Let's do an example. Okay. Let's move on. Okay, yesterday we have seen implicit differentiations, and we got good questions. I got good questions. How do you know? If you remember yesterday, we tried to solve z to find the derivative of z with respect to x, and z with respect to y. And then you have all good questions that how do you know if z is a function of x and y, or x is a function of y and z? And what did I say? I said it's an assumption that you made that z is a function of x and y. Okay, I said this is an assumption. Otherwise, it's totally valid to seek the partial derivative del y del z. I mean, there's nothing that forbids you of doing it, right? It's the same. It's the same concept. You have to solve for y in terms of x and z, and then you find the partial derivative. Okay, so and then if you remember I found a nice example. Maybe we can do it again. Okay, something like that. We could do an example like the previous one. I found one in the book. I ran out of ideas. Now the book gave me an idea, so we can do it. But anyways, afterwards. Okay. Now let's have my notes here. Okay, so as an example, we start with if you have x squared plus y squared is equal to 1. Does this define y as a function of x? Is y a function of x here? No, because what is the sketch of this curve? It's a circle, right? So can you really define y as a function of x? No, because it doesn't pass the vertical line test, right? Now, if I tell you I choose this point. Choose this point. And I tell you near this point. For example, here. Can you express y as a function of x?
Yes.
What is y in terms of x on this side? Y is what? Square root of 1 minus x squared. Why did you not hesitate? Why do you not hesitate? What's the logic behind this? Well, immediately y is square root 1 minus x squared. You just solve for y, exactly. So you know that y squared is 1 minus x squared. Now you notice here that for every point here, what can you say about the y value? Y is positive, right? If y is positive, you solve for y in terms of x. Now you couldn't solve it, you couldn't express y as a function of x, but you could, in general, but you could express it near a point, right? Now if I tell you near this point, how can you express y as a function of x? Choose a point here. How can you express y as a function of x? Near this point. Yes? Someone said it? The same, right? Because y is positive here, so near this point, if y is square root of 1 minus x squared. Agreed? Now I pick this point. What is the value of y? What is y in terms of x near this point? Here, for example, we take here. What is y in terms of x on this arc? negative, sorry, if y is negative, minus square root of 1 minus the square. Do we agree here or not? So we could solve for y in terms of x, and we can also find the derivative, provided that my x is neither 1 nor minus 1. Right? You see that? So if you differentiate this, or let's do implicit differentiation. 2x plus 2y prime, 2x plus 2y prime is equal to 0. Right? Agree or not? So what is y prime? Y prime is minus x over y. Right? Or we can do it with the same formula as before. Now, if x is 1 or minus 1, what is y? If x is minus 1 or x is 1, what is y? 0. So can you find the derivative if y is 0? Okay. And your derivative theory tells you that is this differentiable at x equal 1? No. Right? This is not differentiable at x equal 1. And neither at x equal 1 nor at x equal minus 1. Okay? So provided my y is non-zero, so basically around any point here that is neither minus 1, 0 or 1, 0, you could find the derivative. You could find dy dx. Do you agree or not? This is calc 1. Awesome. Now in calc 3, we saw another example. So z squared is equal to 1. Does this define z as a function of x and y, this general term? No. Why is that? For example, if you pick, I don't know, 0, well, if you pick 3 terms, no. Well, that's 1 half plus 1 half. So if you pick 1 half, x equal 1 half, y equal 1 half. What's the value of z here? So x squared is 1/4, y squared is 1/4. You add them both, you get 1 half. What is the value of z squared? 1 half. So how many values of z that correspond to these two? 2 values, right? So what do you have? You have z is equal to 1 over root 2, or z is equal to minus 1 over root 2. You agree or not? Yeah? So far so good? Does this define z as a function of y? F(x) and y? Does this, if I tell you this, does this define z as a function of x and y? No. Okay, very good. Now, if I tell you that z is positive, so if you pick a point, this is the sphere, and you pick a point here where z is positive, can you write z in terms of x and y if I give you that z is positive? You're given that z is positive. What is z in terms of x and y? Square root. If z is positive, if the square root, if z is negative, if z is a negative point, if z has a negative value, what is z in terms of x and y? Z is so if I give you a point here, I tell you around this point, can you express z as a function of the x and y just near this point? Can you do that? If I fix a point where z is strictly negative, you can do that, right? Because near this point, will still be strictly negative. You will have problems if z is equal to 0. Right? When you differentiate this may not be differentiable at 0. Do you agree? What is the derivative of del z del x with respect to del z del x? What is that equal to? Minus x over, what is that? Minus x over z, is that it? Right? Minus x over z. And del z del y is minus y over z. So if z is equal to 0, you'll have a problem with the derivative. And in fact, if z equals to 0, you have these two expressions. Well, it's equal to square root and minus the square root of 1 minus x. Okay? But anyway, let's not worry about this. But this is the idea. So the implicit function theorem will generalize this thing that we have done and find conditions under which you can solve for z in terms of x and y. Now we will do it not only with 3 variables, but we'll do it with like 4, 5, 6, 10 variables. So if I give you a system of equations, well, let's do a motivation now, small motivational example. Suppose that I have, consider the following system. Okay, this is still motivation, it's not very rigorous. And you have this one, x, y, z, well, what did I use here? F, x, y, z, and w is equal to 0, and g, x, y, z, and w is equal to 0. Okay, so you have 2 functions equal to 0. This is a system of how many equations? How many equations you have? 2 equations, right? And how many unknowns? 4. Okay, now suppose, I'm saying suppose. What do I have in my notes? Let me stick to my notes. Suppose that x is a function of z and w, and y is a function of z and w. So z and w are independent variables. I'm giving you this, okay? I'm giving you that z and w. Independent variables. And x and y are functions of z and w. Okay? I'm giving you that x and y are functions of z and w. Is this clear? This is like we have done before. I'm telling you that z is a function of x and y. Now I'm telling you that x is a function of z and w. Y is a function of z and w. Great. So with what are we going to differentiate? With respect to what are we going to differentiate here? Z and w. So let's try to find which one do you want? Del x, del w, or del x, del z? Del x, del z? Sure. Let's try to find del x, del z. And del y, del z. Okay. So with respect to what you need to differentiate here? Z. Let's differentiate the first equation with respect to z. Keeping in mind that x is a function of z and w. Z and w are independent variables. So x, y, z, w is equal to 0. X, y, well here, keep this in mind. Differentiate with respect to z. You can write this if you wish. Okay? X is a function of x and z and w. Y is a function of z and w. Z is z and w is w. Differentiate this with respect to z. Who wishes to help me? Who wants to help me? I'm stuck. How do I do it? How do I differentiate? X is just a function of z and w, and differentiate with respect to z. Chain rule. This is just the chain rule. Yeah, yeah.
What do you do? Del x over del z.
Del x, del z. Okay.
Del
respect to what argument? The first argument, which is f1, right? f1, right? f1 of what? Exactly. Plus. Are we good here? The first term is good. Differentiate this one with respect to z. Derivative of f with respect to the first argument applies x, y, z, and w. Agreed? What's the second term? Del y, del z. Yeah? Okay. Plus, what's the third term? Everybody, what's the third term? Plus? F3, x, y, z, w. Why is that? What's the term? Yeah?
Then it's just one.
Del z is 1. And what's the fourth term? What's the fourth term? Del w del z is what? Yes? Many people are saying it. Del w del z is 0. So the fourth term is 0. So this one. Okay. Now we need to find del x, del z, del y, del z. Is that equation enough? You can suppose that this is known, and this is known, and this is known. How many unknowns do you have? 2. You have one equation and 2 unknowns. Is that enough? Do you have another equation that you can use? Yes. Those are known. F1 and F2 are known. Because I'm giving you F. F3 is known because I'm giving you F. If I give you F, you can differentiate it. Right? You agree with this? If I give you F, you can find these. But is that enough to determine del x, del z, and del y, del z? What do you need? I need another equation. Where does the other equation come from? G. So let me differentiate this with respect to z. What do I get? Could you just read this from there? The same thing, but with my g's. Exactly. We agree with this, everybody? Everybody. Del y, del z, g1. Plus. Oh, okay, this is del x, del y, del z. G2 plus G3 y z w z w is equal to 0. Now, how many unknowns do I have? Del x, del z, del y, del z, del y, del z, del x, del z. Agree? 2 unknowns. How many equations do I have? 2 equations. Okay, so what could I refer to here? My linear algebra, right? We see that? How can we write this as a matrix? We write this in matrix form. We write this in matrix form. F1 XZW, YZW, ZW, F2. And then what do I have here? G1. times what? Times what? Del x del z. X and del z is w. Z is w. Is equal to what? To minus f3. Okay, minus f3. I mean, you know what the arguments are. Okay, just two. Do you agree with this? Do you agree with this matrix operation? Well, this matrix transformation. 2 by 2 matrix. 2 by 2, 2 by 1. I get 2 by 1. You put these on the other side, and you write this in this matrix form. Agree or not? Yes? We agree with this? Linear algebra, we agree with this form? No. When do I have a unique solution? Suppose that this matrix is invertible. When is this matrix invertible? If its determinant is non-zero. What's the determinant of a 2 by 2 matrix? It's AD minus BC, where A, B, C, D, right? So if AD minus BC is non-zero, I can solve for del x, del z, and del y, del z at a given point. Do you agree? Everybody, do you agree? And then I can find the derivative. Now here I assume that I could solve for x, y, and z, for x and y in terms of z and w. The theorem tells you that if this matrix is invertible at a given point, and you have some minor continuity restrictions on the f's, basically all the f's that you will see are continuous and differentiable infinitely many times, say, then you can solve for x in terms of z and w, and for y in terms of z and w. And the derivatives of x and y with respect to z are given by this system. And the derivative of x with respect to y, x with respect to w and y with respect to w are given by another system, which is derived in the same. Okay. It's not easy, but let's, yes. Yeah. It will just change to, so del x del w here, right? And here you will have a 4, right? Exactly. You see that? And then the del y will be with respect to w. Everything will be with respect to del w. Okay? We will say this theorem now, and now there are formulas for this. Now, do you want to remember bad formulas, or just rederive everything? You can solve a system, right? You know how to solve a system. I personally don't remember any formula. I resolve the system every time. And if I ask you to solve for del x, del z individually, how would you find this? You can do it by Cramer's rule, right? Do you remember Cramer's rule? No? Okay, so we'll try to avoid it as much as possible then. But this is this is linear algebra again. Did you see Cramer's rule? You didn't see it. So if you have a system, you look at the determinant of the coefficient matrix, right? And then if you're looking for the first variable, you replace the equal sign. So if you have ax equal b, how you get the first variable for x? You switch. No, you didn't see that? Okay. Well, who saw Cramer's rule? You know, I'm linear algebra, math 133. You don't see this? You all took math 133?
Maybe we don't know the name. Maybe we don't know how to start.
So basically, okay, I'll try to avoid it. Okay, I'll try to avoid it as much as possible. Okay. Now let's lay down the theory for this. we'll lay down the theory for this. So this theory is going to become handy later on in the course, so we'll do it now. Okay. Now the first definition. Yeah, I mean I don't know why I chose to do this part, but I guess so. Usually they may do it or may not do it, but this is I think the most interesting part of the course for me at least. But anyways, yeah. So I think it's in Adams, but not in Stewart. Okay, Adams has some good stuff on it. And Stewart doesn't have the same one. But yeah. Anyways, so let's start with the first definition. The Jacobian determinants. Okay, now forget about everything. We'll get back to this. Suppose our functions of x and y the Jacobian determinants of U and V with respect to x and y is denoted by del uv over del xy. I mean, let me just make sure that I have it correctly. How did you know determinant? Did you know determinant by big brackets in calculus? So in linear algebra, did you know it by this way? Yeah, that's how you know determinant. Okay. This is del u del x, del u del y, del v del x, del v del y. So this is a function. And what is that? Determinant of 2 by 2 matrix AD minus BC. Now this determinant, I mean someone asked a very interesting question yesterday, maybe we can answer this. Maybe we'll be able to answer this. And let's do a small example. I have a small example here. Let x equal r cosine theta, y is equal to r sine theta, where r is positive and theta belongs to 0 to pi. Wow. Find del xy over del r2. What is this? You get stuff, but this is easy. This one is easy. This one is easy. So del x del y over del r theta. How do you do this? This is just the determinant. What is del x del r? I mean, let me write it. What is del x del r? What is del x del r, everybody? Del x del r is what? Cos theta. Del y del r is what? Sorry, no, this is del x del theta. Del x del theta is what? X, first variable, 1, 1. So it's del x del r. Del x del theta. Del y del r del y del theta. Now if you mess them up and you write these two here, Is it going to change the answer? No, because if you transpose the square matrix, the determinant change. No. Okay? But it's better to stick to it this way. What is del x del r? Everybody, del x del r is what? Cos theta. Del x del theta is what? Negative r sine theta. Here, del y del r sine theta. And here is r cos theta. What is this determinant? R cos squared plus r sine squared. What is that? R cosine squared, right? Plus r sine squared. Linear algebra. Determinant AD plus r sine squared. Okay? So far so good. Easy work. Let's see if I can find a nice example. Are we good here? Okay. Awesome. This is R, which is always positive. Now really, this plays the role, so yesterday I got a good question on how can you manipulate, like, why, anyway. Yeah, I don't know if I should say this, but so some of you noticed, that's not work, okay? That's not work. We'll worry about this later. We'll worry about this later. I mean, you know, it's a very interesting remark that I got yesterday. And the idea, what's the idea of this Jacobian business? In one dimension, when you did integrals, you chose a change of variable, right? You said u is equal, say, f of x, then du is f prime of x dx, right? Now here, we're going to do double integrals later on. So a change of variables will involve two variables. Now when it involves two variables, how do I compute the derivative? This will come into play. Okay? We do one more example. Let's do one more example. Find the Jacobian. Del x y over del x t. And let's do something interesting. Del x t over del x y. If x 2x minus t and y is 3x plus t. So what's del xy over del x? It's what determinant? What is the determinant of this one? So it's del x del x. So I take del x del x. What is del x del x? Del x del x is what? 2, right? Now I have del x del t. What is del x del t? Minus 1, right? Del y del x. What is del y del x? 3. What is del y del t? 1. So what is this determinant? 3 plus 3 is AD. 2 plus 3 is 5, right? We agree? Okay. Now, I want to find del x, del t. I want to find now the Jacobian of del x t over del xy. What would be an ideal scenario? What would be very ideal? Like, if you were to get an answer. 1 over 5. If you were to guess an answer, right? If something were ideal, if you could treat these as numbers, what would be the, right? So what is x in terms of x? How can you solve for s in terms of x? So let's add them up. What do you get? You get 5s is equal to what? Add them both. What do you get? 5s is x plus y, right? Agreed? Add them both, you get 5s is x plus y. So x is what? X plus y over 5. And what is t? You can subtract that. So t is, let's see, what did we use? It's x minus 2s, right? T is x minus 2s. What is x? So it's x minus x plus y over 5. So what is t? 4x over 5 minus y over 5. Is that right? Did I mess it up? I missed a 2, right? I missed a 2x, so it's 3x over 5 minus 2y over 5. Are we good so far? Okay, so what is the Jacobian of s and t with respect to x and y? It's del x del x, del x del y, yeah, times del t del x, del t del y. Determinant. What do you get? Del x is what? Del x is what? Differentiate s with respect to x. What do you get? 1 over 5. Differentiate s with respect to y, what do you get? 1 over 5, right? Differentiate t with respect to x, what do you get? 3 over 5, right? And differentiate t with respect to y, what do you get? Minus 2 over 5. Determinant. Minus 2 over 25 plus 3 over, no, wait, there's something wrong. Del x, del t, del y, del t, del x, so did I mess it up? So, x plus y over 5, that's good. What is t? What is the mistake here? T is 2s minus x, right? T is 2s minus x, right? It's minus here, 2 here. So t is minus 3 over 5 plus 2 over 5. Del t del x is minus 3 over 5, and del t del y is 2 over 5. Great, now what do you get? You get 2 over 25 plus 3 over 25. That's 5 over 25. What is 5 over 25? 1 over 5. Okay. It's weird. Now, there is something striking here. Something should be striking. What is del x, del x? Del x, del x, what is that? 1 over 5. What is del x, del x? Del x, del x is there. What is it? No, del x, del x. xs. Del x, del x. 2. What is del x, del x? Del x, del x, what is that? 1 over 5. What is del x, del x? 2. There's something striking here, right? What is something unusual? And one variable, if dy dx is something, what is dx dy? It's 1 over dy dx, right? Here, is it the same? Can I invert del x and del s? Can I say 1 is, Okay. Someone asked me like a question yesterday about this. really you cannot manipulate these things together. You cannot say del x del s is 1 over del s del x. You cannot do that. But, let's do something here. If I ask you to invert this matrix, when you invert this matrix, what do you get? So how do you invert this matrix? You take the determinant, 2, minus 1, 3, 1, inverse. What is that? 1 over that A, which is 1 over 5, right? Times, what happens here? I flip A and D, right? So 1, 2, and what do you do with B and C? You flip I flip this sign, just let me get. Look at this matrix. And look at the inverse of this Jacobian. This is very cool, actually. I like this. Right? So you cannot really say del x del s is 1 over del s del x. Someone asked me a question yesterday, and I thought that maybe we would address that. Because usually when you say del s over del x, many of you say del s over del x, and I don't repeat the same thing, usually. Right? If you notice, I just say del x del s. So now when you say del x over del s, really you cannot treat this as a number. But what you can do operations with is this Jacobian. So del xy over del st inverse is equal to del st over del xy. We can show that. Maybe we won't show that, but we will just assume it. But this is an example where you cannot play with del s del x and del x del s. Okay? Is it clear how this Jacobian business? Is it clear?
Yeah.
Okay. Now we move on to the statement of implicit function theorem. Okay, so someone asked a very good question yesterday. I didn't answer him this way, but now I think they have the answer. That really you cannot manipulate these things as number. If you want to consider inverses, you have to consider of the whole Jacobian. Okay? Are we good? Yes. Well, if you want to consider derivatives, right? How many derivatives do you need to consider? So you have x is a function of r and theta, and y is a function of r and theta. You need to consider all possible first derivatives. So x with respect to r, x with respect to theta, y with respect to r, and y with respect to theta. Now, if you can solve for r and theta with respect to x and y, you can consider these two. Okay? Very nice. We will work, this will come in handy later. This is why I'm doing it now. So we can save time later. Now, the statement of the implicit function theorem. And define Jacobian for two variables, right? So let me just define Jacobian for many variables. So suppose xy, say, and dxy are functions of several variables. You can restrict your attention to the Jacobian with respect to the first two. Okay, so you can consider del u v over del x y. This is just del u del x, del u del y. Okay, really, it's the arguments that matter. This can have more than one variable. Okay? This can have more than two variables. Del v del x, Okay? This Jacobian business is clear, right? There is nothing about implicit differentiation yet, right? Differentiate stuff, compute a determinant, that's it. Okay. Now it's the big theorem. Now it's a long theorem actually. Great. So let's remember the three-dimensional variable, the three variable thing. How many equations I had? I had fx, y, z is equal to 0, right? And how many variables did I want to express in terms of x and y? Z, right? And how many equations did I have? 1. Okay? Now, if I want to express z and w, let's say, if I want to express z and w as functions of x and y, how many equations do I need? 2. Okay? This is the thing. Now we will, okay. Okay, so this is a bit notation heavy. You can just focus on it. But we'll just do it. Okay. Again, always let's remember this example. Okay, x, y, z and w, or x, y and z. Suppose, consider the system of n equations with n plus m variables. I have f1, x1, xn. Wait. Yeah, okay, maybe well, that's fine. N plus n doesn't matter. Y1 up to yn is equal to 0. How many equations is this? This is a function, a real valued function. How many equations? This is 1. I need n equations. How many f's do I need to have? Okay? And how many of them do I need? I need n equations with n plus m variables. So what is the last equation I need to write? How many equations do I have? N, right? I have n equations. Fn. Good? I have n equations in how many variables? N plus m. M variables, n variables. So far so good. Remember, you want to express z in terms of x and y. How many equations you had for z in terms of x and y? You had one equation, and you want to express z in terms of x and y. One equation is enough for you. Okay? Great. Now, of course, here I will say where f1, f2, fn are functions from R n plus m to R. So each function is a real valued function and has n plus m arguments. Now suppose P is a point P0, say, A1, A2, AM, B1, BM, is a solution to the system, to the above system. For you, it's above, the above system. Suppose, moreover, that suppose moreover that, now let's pay attention, F1, F2, up to Fn have continuous partial derivatives with respect to x1, x2, y1 up to yn, and suppose that, okay, now it's near P, well, I mean near P0, let's say near P0, that's fine. And suppose, okay, now we're going to make the command here is big, huh? The Jacobian of f with respect to y, and suppose del f1, f2, fn, L, y1, yn at P0, or you know, if I write P0, is that okay? You understand it's just A1 up to AM, B1 up to the N, is that fine? Or I just write A1 up to AN? P0 is fine? At P0 is different than 0. Then, what time is it? 12:30? Okay. Then, the y's can be solved in terms of the x's. This is what this statement says. You can solve for y in terms of x. I mean, this is a bit striking, right? You have n equations and n plus m unknowns. It tells you that if this derivative is non-zero, if this Jacobian matrix is non-zero, then you can solve for y in terms of the x's. Then, the system can be solved for y1, yn in terms of x1, then near P0. And what is the derivative? Or you know, let's write this. In other words, is that clear what it means? Y, you can solve for y in terms of the x's. You can write y in terms of x. y1 as a function of the x's, y2 as a function of the x's, y3 as a function of the x's. Do I need to specify what this means? Sure, let's specify that. In other words, so I don't know if they do it in 264. I don't know if they do it in 264, but in 264 the statement is way shorter than this. Okay, you don't write f1 as fn, you just write one big function f. Anyway, in other words, we can find function phi1, phi2, phi n that. y1, y1, x, y, f, y2. And yn near T0. Wait. Or touch that. I mean, so I will tell you what's a difficult question, okay? You should not worry about the question. Touch that. Touch that, touch that, touch that, touch that. So if you plug in, what did I use? I used A and D, right? Touch that. D1. Up to Bn is phi n. A1 up to Am. And yeah, I mean, so do you guys want a formula for it? I prefer not to give a formula because you will mess it up. Okay, a formula involves Kramer rule. Do you want a formula with Kramer rule or not?
Please.
Formula. And oh man. Del yi del xj. Del yi del xj. Okay, so I even don't know the formula by heart, but minus del at say d0 here. It's the Jacobian evaluated at d0. And by Kramer's rule, so let's see, this is, I have yi here. No, I have yj here. Yeah, I have yj. yj. So yi. Yeah, I don't even know the formula by heart. Yj. And it is, what do I have to say? Del f1. What does it do? Yeah, then. Over. Del. You keep the same until yj is switching to xj. And then y. Let me make sure that this is true. Yeah, okay, this is true. So no, this is yi. No, this is yi. Yeah. This is yi. And the I position, you have xj instead of yi. I mean, look at this minus del over the del. What does it look like? It reminds us of a formula, right? Yeah. It reminds us of, so you remember when we had z in terms of x and y, what did we have? We had minus f1 over f3 for del z del x, right? And for del z del y, we had minus f2 over f3. So let us do this with respect to x and z. It's tough. This is not easy. This is not easy. Again, I prefer 100% that you rederive this instead of knowing this formula. I mean, I don't know it by heart. So like, you know, it's I rederive it every time. It's Kramer's rule, definitely. But let's do an example. So it tells you that y could be solved in terms of x and z. y1 up to yn can be solved in terms of x1 up to xm. Now remember, if I have one equation, fxyz is equal to 0. What do I need to solve in the terms of two others? I need to solve for z in terms of x and y. Okay? So I need the derivative of f with respect to what argument here? So what is my n here? Z in terms of x and y. What is my n? How many y's do I have in this statement? I need to solve for y in terms of x. How many y's I have? 1, right? I mean, it's different than y here, but anyway. So how many variables do we need to solve in the term of two others? In terms of two others, 1. So you have, so this is just del f, del z. At the point P0. Great. Now, on top, n is 1, so I must be 1. So if you want to solve for del z, del x, if you replace the z by x, you get minus del f del x at P0 over del f del z at P0. Okay? This is how you get it. It's a bit tough. It's a bit hard to understand with the notation, but we will make sure to. It's gonna get harder with the notation as well. But anyway. Yes. Pardon me? Could you guys, yes?
The numerator.
I have up, yes.
Just explain how you got down.
xj here at the I position. Kramer's rule. Kramer's rule. You need to solve for the I variable, right?
Yeah.
You know Kramer's rule? This is just Kramer's rule. Okay? Kramer's rule. Okay? So what do you have? You have a system of equations. Write the whole thing down. Okay, write the whole thing down. F x1 up to xn, phi 1, phi 2, phi n, and differentiate every one of them. You'll get a system of n equations with n unknowns. And Kramer's rule tells you this. Yeah. N equations, no. Wait. Yeah, sure. Well, if you differentiate with respect to one x, choose the x you want to differentiate with, right? So if you differentiate with respect to x1, you will get n equations with n unknowns. Okay? How do you find in the column vector the ith one? You take the determinant of the matrix of coefficients, and then you replace it by, and then on top, you take the determinant of the matrix where the ith column is replaced by the coefficient of the matrix. Okay, it's not easy. It's not easy. I mean, we will do an example. Don't worry. We will do an example. Okay? We will do an example and explain how you get it. Okay? I think showing it by example is easier. Great. Let's pick one from the book. Maybe we can do one from the book. I think. Okay, so that's the system. xy squared xzu plus yv squared is equal to 3. And then x cubed yz plus 2xv minus u squared v squared is equal to 2 can be solved for ub in terms of x, y, and z near the points 1, 1, 1, 2, 3, 4, 5. So I'll just say in what do we need? We need x, y, z, u. Okay. So basically, this is x, this is y, this is z, this is u, this is v. Here it doesn't matter because they're all ones. Okay. Very good. So first of all, let's do a check. Does 1, 1, 1, 1 satisfy the system? Plug in x, y, z equal all 1. What do you get? 1 plus 1 plus 1, what is it equal to? 3. 1 plus 1 minus 1 is equal to? So it's 1 plus 2 minus 1 is equal to? 2, right? So 1, 1, 1, 1 satisfy the system. This is the first step. Okay? It's clear that, so an exam I might tell you, show that the point blah 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 satisfies the system. You get 2-3 marks just to plug in. Okay? And compute something nice. Okay. Now, notice that I don't know what the function is. I don't know how I can express u and v in terms of x, y, and z. I don't know how to explicitly do that. But I know that I can do that provided the Jacobian is non-zero. Right? And that's another question. And find del u del x. What does the book do? I want something. Well, this is dangerous because I don't know how this will work out. But and find del u del x, del u del y, del u del z at 1, 1, 1. Okay, I don't know how this will work out. Worst case, we write a system and we leave it in a system. No, that's going to be 3 systems, right? You differentiate with respect to x, you get a system of 2. Differentiate with respect to y, so that's just right. That'll be nothing. Okay? Just 1 second, please. Del v del x. Yeah, okay. Oh, so that's right. Okay, first, I need to write my system, something is equal to 0. Here it doesn't matter because the right-hand terms, the right-hand side is constant. But let's write this. What is F1 here? X, y, u, v. What is that equal to? This is x, y squared minus what? Plus x, z, u plus y, v squared minus 3, right? And what is my x2? What is that equal to? X cubed yz plus 2xv minus u squared v squared minus 2 is equal to 0. Here I have it equal to 0. I have a solution to this point. I have a solution to this system. What is the solution? 1, 1, 1, 1, 1. Okay? Now, the question is that, can I express uv in terms of x, y, and z near this point? What do I have to compute? I have to compute the Jacobian with respect to u and v. Now let's, something maybe we should worry about. If I differentiate f with respect to each argument, do I get continuous functions? These are polynomials, so you differentiate, but you get continuous functions, right? So these are f1 and f2 have continuous partial derivatives. Okay, first order partial derivatives. Now, what do I need to compute? I need to compute the Jacobian of f1, f2 with respect to u and v at one point, which is 1, 1, 1, 1, 1. If that Jacobian is non-zero, it means the answer is positive. I can solve for u and v in terms of x, y, and z. That's it. That's the answer to this question. I'm not telling you to express it. I'm telling you, can you express that? If the Jacobian is non-zero, then the answer is yes. By what theorem? Implicit function theorem. Very good. I felt like I lost 100% of that class, but at least one person followed. So that's good. Okay, let's do that. So let's compute del f1, del f2 with del uv. What is that? Notice how many functions you have. How many functions you have? 2. How many functions you need to express in terms of the other? How many variables you need to express in terms of the other? 2. Okay, this always should be a square matrix. Okay? What is that? This is del f1 del u. What is del f1 del u? Can you help? xz, right? Del f1 del u is xz. Right? Let's evaluate at the point p0, say. This is xz. And then del f1 del v. What is del f1 del v? Blah 2vy, right? Del f2 del u. What is del f2 del u? Goes away. You get 2u v squared minus 2u v squared. This is the determinant of this matrix. Minus 2u v squared. And then what do you get? This is the derivative, yeah. The derivative with respect to v, and it's 2x, minus 2vu squared, right? 2x minus 2v u squared. As p0, as 1, 1, 1, 1, 1, 1. Replace this, what do you get? 2, so you get 1, 2, minus 2, and 2 minus 2, what do you get? 0. What is the determinant? No, I think I messed something up. xzu. What is x? Oh, so I differentiate this one with respect to u. You get xz, right? Yeah. And then I differentiate the same one with respect to v. 2v. Is that the same system I had written or not? No, this is good. Is this good or not? Yeah, what is the determinant? 4, right? Did I say 1 before? I said determinant is 1 or determinant is 4? I didn't say anything. Did I say something? What is the determinant? 4. So, can you solve for u and v in terms of x, y, and z? Why is that? By the implicit function theorem. Different than 0. By the implicit. Function theorem. We can solve for uv in terms of x, y, Now, what do I need to find? What did I say? Del u del x and del v del x? Is that what I asked? Great. Del u del x. How do I find del u del x? What do you do with these two functions? You differentiate with respect to x by keeping in mind that u and v are functions of x. You agree that? You can solve for u and v in terms of x, y, and z. So u and v are functions of x, y, and z. Okay? Yeah, so far so good. So I want to find del u del x. Need them. Okay, I mean, I will write a notation how to imply that u is a function of x, y, and z. So you write del u del x, okay, and you write y, z here. So u is a function of x, y, and z. So x, y, and z are independent variables. This means that this means that u is a function of x, y, and z only, and v is a function of x, y, and z only. Is this notation clear or no? Right? So u is a function. What are the independent variables? The independent variables are always down. X, y, and z. X, y, and z. Those are the independent variables. Okay? U is a function of x, v is a function of x. It's tough. Yeah, sure. But again, it shouldn't stop us. Okay, now I have a problem. I need to write. I'll keep it here. Differentiate this one with respect to x. Differentiate this one with respect to x. What do you get? Everybody. The independent variables are y and z and x. So I differentiate the first part with respect to x. What do I get? Who can help me? First term, what is it? Y squared. Plus, does z depend on x? No. So we can take it out. xu, how do I derive it? Product rule. xu plus, so z. How do I differentiate xu with product rule? It's u plus x del u del x. Right? Now, y, does y depend on x? Y is a constant. So when I differentiate y v squared with respect to x, I can take the y out and just differentiate v squared with respect to x. What is the derivative of v squared with respect to x? It's 2v del v del x, right? Is equal to 0. What do I have in my unknown? Del u del x, del v del x. Agreed? How can I find now you have a system with two equations, with one equation with two unknowns. Can you find del u del x and del v del x? One equation and two unknowns. Can you find them? What do you need? Exactly. So let us rearrange this nicely. So I get zx. I mean, this part has nothing to do with the part before. Okay? This part you can solve without resorting to the previous part. Okay? You see that? So zx del u del x plus 2yv del v del x. Okay, notice something. Look at the Jacobian we computed first. Okay? Can you look at the Jacobian? I erased it, but can you have a look at it? Did you look at it? What is the first term of my Jacobian? Zx, right? You see that? What is my second term? 2yv. Here it is. Is equal to, what do I have here? Minus y squared minus zu. Now, if I differentiate the second equation, anyone can help me, or we should rederive it. We rederive it? But what is the Jacobian I had before? The Jacobian I had before. So you notice that this is the 1-1 entry of the Jacobian. This is the 1-2 entry of the Jacobian. Here, if I have del u del x, what will my entry be? So it's 2-1, right? And here it will be the 2-2 entry. Okay, now what is del u del x? So let's differentiate this. Let's differentiate this with respect to x. 3x squared yz, right? You agree? 3x squared yz. So this will go here. Plus 2xv. What is the derivative of 2xv? Let me write this one here. So 3x squared yz plus 2xv. What is this derivative with respect to x? Who can help? What rule do you use? Product? Everybody's confused. That's fine. You'll practice it and then we'll get over this. So 2xv, what is that? That's 1 times v plus x del v del x, right? Minus u squared is a function, so I have two functions of x, so it's minus 2u del u del x v squared minus 2v del v del x u squared is equal to 0. Okay, so let me collect terms that have nothing to do with del v del x. So I have minus 2v, I put it here. Minus 2v. Yeah? And then everything else has a del v del x or a del v del x. So del v del x, I have 2x del v del x minus 2v u squared del v del x. Is that my fourth term in the Jacobian? 2x minus 2v u squared. Is that my diagonal term? Yep. What did I say? It's 2v minus 2v u squared, right? 2v minus 2v u squared. Then, what do you have here? Del u del x, what is my term in del u del x? I have minus 2uv squared. Is that what I have? Is that what I have? I have my system. How many unknowns do I have when you plug in 1, 1, 1? Del u del x, del v del x, del v del x, del u del x. Okay? This formula this weird formula that I wrote tells you this: the coefficient of the matrix is a Jacobian, and these are the derivatives with respect to x of the non-Jacobian, like the terms that do not appear in del u del x. Okay? The formula is very bad to remember, unless you like to remember it. I prefer that you don't remember it. So let's see. For u, v, for what do I get? I get 1. What is my Jacobian? Can anyone? So it's 1, 2, minus 2, 0, right? It's 1, 2, minus 2, 0. Not determinant, but the Jacobian matrix, what is it? It's this one, right? Times del u del x, is it del u del x and del v del y, del v del x is equal to what? To minus 2 and then minus 5. Is that right? Minus 2 and then minus 5, is that right? Is that it? You plug in x, y, z. The good news is that you don't need to solve, you don't need actually to find u and v in functions in terms of x, y, and z, because that might be a tougher thing. That might be tough. I mean, we saw the example with x is 2x minus t and y is 3s plus t. This was easy, right? Now here it's tougher. This is the good news. The bad news is that you will have to know this. Okay? This is, I guess it's not very bad news, because it's not bad actually. It's easy, more or less. Once you practice 5 or 6 times, you will master it. And you will see the pattern. You will recognize the pattern. Okay, you will say, okay, I will not do this system. I recognize this is Jacobian. I recognize this is this matrix. Now, how do you solve for w del x at t0? Say here at t0. How do you solve for this? How do you solve for this? System of equation. You invert this matrix and you multiply by minus 2 minus 5. Let's do this. What time is it? 20 minutes. 20 minutes. Del u del x, del v del x at t0. What is that equal to? It's 1, 2, minus 2, 0 invert. I mean, why did I want my Jacobian to be non-zero, to be invertible? My determinant must be non-zero. If the determinant is non-zero, what can you do with the matrix? You can invert it, right? And solve the system. How many solutions does del u and del v have? One solution, because this matrix is invertible. Yes, sir.
I have a question.
Yeah.
When we get the two systems of equation, can you just not plug in the point and then just solve the system of equation?
Sure. Yeah. Yeah, exactly. This is what I'm doing, right?
I don't know, instead of multiplying the addition, just plug in x, y, z and your value is 1, 1, 1, 1. And then just solve for
Del u del x and del v del x. Same thing, right? It's the same thing. You see that? Did I use Kramer rules here? No, right? It's the same thing. Now in that case it's easy because you have a zero coefficient, right? So this is easy. So you can find actually you can read off one of the terms, right? You can read off the del u del x. What is del u del x? Can you read it from here? Minus del u del x is minus 5. Minus 2 del u del x is minus 5. So del u del x is 2 over 5. Right? You see that? In that case, it's easier to solve actually. You can just, you see what I'm saying? You don't need to write this as a matrix because del u del x is already given to you. So you get minus 2 del u del x plus 0 del v del x is equal to minus 5. So you know that del u del x is 5 over 2. And then you can find for del v del x. But I'm writing in a more general way, okay? Because maybe I give you a 3 by 3, for example. Okay? Minus 2 minus 5. Okay? And then it's a good linear algebra reminder. So, I don't know if we should do one more example like that or chain rule. What do you guys want? Chain rule? So let's see how to invert this matrix. Again, this stuff you can avoid doing this, right? Just you can avoid doing this. You can solve immediately from here, as your friend pointed out. But let's invert this. How do I invert this? What is the determinant? It's 4. So it's 1 over 4 times what? You flip a and d, right? 0, 1. You flip a and d, and you minus 2 times minus 2. Minus 5, what do you get here? What do you get? 2. So you get 2 over 5, wait, yeah. So you get 10 over 4, which is 5 over 2, very good. 5, 10, yeah, so 10 over 4. 10 over 4, and minus 4, minus 5, what do you get? Minus 9 over 4, is that right? So let's plug in 10 over 4 here. 10 over 4 minus 2 times 10 over 4. No, wait a second. Minus 2 times, yeah, that's minus 5, very good. And let's plug in minus 9 over 4, so it's 10 over 4. 10 over 4, what do you get? Plus, or no, minus 18 over 4, which is minus, wait. Oh, no, that's fine, yeah, that's fine. Okay, this is good. Okay, I just checked that you get the right answer. So what is del v del x? 10 over 4. What is del v del x? Is minus 1 over 4. It's clear. Do we know how to solve this equation or not? Yeah? Yes. Yeah.
It's like del u over del any of the independent variables.
Yeah.
So we can write like the Jacobian times the column of matrix of del u like over del y. It's basically del y.
Okay.
So it would be the same thing, but then it would be equal to something else.
Yes, exactly.
Okay.
Exactly. The matrix coefficient is the same. There's something else that's different.
Yeah. So it needs to be
You have to differentiate it with respect to y. Yes. For this one, yeah, sure. Many questions. Yeah. But I don't know if Woburg has. them. But if Woburg doesn't have them, it's easy to make up questions. Right? I just give you two systems. Now it's easy to make up questions, but it's not easy to guarantee that the answer is nice. Okay, so I will just give you like questions, and then you can do some matrix linear algebra. Okay, so should we do one more like that or chain rule? One more like that? Sure. Let's see if the book has some of that. Okay, maybe I'll give you more of the notation. Okay, so this is from the book, and then you have to tell me what are the independent variables. Okay, here. How much time do you have left? 10 minutes. Okay, so 10 minutes is a bit too much for this. 10 minutes is a bit too little for this. But, pardon me?
Do the chain rule and
yeah, I can do a chain rule, and then tomorrow we do implicit function theorem exercise. It's very, very, very fair to assume that you're going to have one long answer on this on the final. Yeah, a long answer, and that doesn't mean you won't have multiple choice on this. Okay? So, yeah. I mean, just to fix some notation, let's take some time to consider some notation, actually. Now if I tell you notation, okay, so if I tell you find del y del x, let me pick u, say. No. Yeah, that's fine. If x what are the independent variables in that case? What are the independent variables? If I give you this, x and u are the everybody. If I give you this notation, what are the independent variables? X and u are x and u are independent variables. And what do I have? Yeah. X and u are independent variables. And what are functions of x and u? Y and X and U are independent variables. So all the independent variables are listed here. What are the functions of X and U? Y and V are functions of X and U. I mean, you know, this is from the book. The book asks us to find this, but I won't. This is just for you to know. Now, maybe I can give you a question. I can give you a question. You can write it down. Show that. Consider the following system. In X, Y, U, V. Show that. What do you prefer? Plus, plus. What combination of two pluses and two minuses do you prefer? Two pluses and two minuses. How do you like to combine them? Plus, plus, minus, minus? Sure. Show that 1, 1, minus 1, minus 1 satisfies the system. Can you solve it? For U and V as functions of X and Y near 1, 1, minus 1, minus 1. Right? 1, 1, 1 satisfies this. Okay? So 1, 1, minus 1, minus 1 is equal to 1. 1, 1, minus 1, minus 1 is equal to plus 0. Right? So it satisfies the system. Can you solve for U and V as functions of X and Y? Sorry, no. What did I have? No. For Y, what did I have? For Y and V in terms of X and U near 1, 1, 1, 1, 1. Okay, this will you will learn how to play with the Jacobian. Which variables to consider, which variables not to consider. Okay, here I'm not asking you to find the derivatives. I'm just asking you to. Can you solve that? Yes, sir.
That's U, right? X and U.
X and U, exactly. Yes, sir.
How do you say you found the independent variables?
Oh, so how do I say? So I have del Y, del X, right? So X must be an independent variable. Near the X, I'll always write a U. So what are the independent variables? X and U. What are the other variables? So Y is a function of X and U. And the other variable is V. V is also a function of X and U. Okay, so I will list all the independent variables here. It's tough. It's not easy. Okay, this is not easy. This is maybe the hardest part of the course. As functions of X and U near 1, 1, minus 1. And find, do it. And find del Y, del X. And del V, del X cubed. At 1, 1, minus 1. Okay. Great. This was fun. Unfortunately, it's an important topic. This is a good question, so try to practice it. And this is kind of very easy, right? The derivatives are very easy here, right? Everything is either minus 1 or 1, right? So U, V, X, X, U, whatever it is, but it's so what do you have to compute here? What should be non-zero? The derivative of which, the Jacobian of which with respect to which variable? With respect to, you want to solve U and V, Y and V as with respect to X and Y. So the Jacobian with respect to Y and V should be non-zero. At the point 1, 1, minus 1, minus 1. Okay? So please, it's very important. I know it's tough. Maybe you will see it in 264 again when you take advanced calculus. Maybe, maybe not. Who knows? But so some of you told me they're not seeing 264. They're not taking 264. Many of you are not obliged to take 264. So I guess it's an opportunity to see this beautiful theorem. Okay? And I mean, here you really can solve for uv and u plus v. Do you think you can solve for them or not? So if I give you the product of two terms, the product of uv is 1 over xy. The sum of u and v is minus x plus y. What can you say about u and v? What equation do they satisfy? U and v satisfy e squared minus plus x plus y t plus 1 over xy is equal to 0. And t, right? You see that? Quadratic equation. See that? U and v are solutions to this equation. And then you can find u and v depending on each case. You guys see this or not? If I give you the product of two terms, and I give you the sum of two terms, how many possibilities you have? If I tell you u plus v is something, and uv is something, you can, to solve for u and v, you can solve a quadratic equation. Have you seen this or not? Yeah? You haven't seen this? So it's sx squared minus sx plus p. You haven't seen that? Okay, that's fine. We can live without this. I'm not asking you to find u and v in terms of x and y. I'm just telling you, show that you can do it. Okay, so on this we will end. I hope you enjoyed this lecture.